So, here's something worth thinking about as you settle in tonight. You are warm. Right now, under the covers, your body is holding a temperature it has kept almost exactly every day of your life. You are giving off heat into the room this very moment, a soft, steady glow of warmth pouring off your skin, warming the sheets, warming the air just above you. If the room could see in the way some cameras can, you would be the brightest thing in it, glowing gently in the dark. And here's the strange part, the part we are going to sit with tonight. That warmth is not a thing. It is not a substance you contain, not a fluid, not a stuff. It is something much stranger and much more alive. For most of human history, people were sure heat was a thing, a material, something that flowed into a pot on the fire and out of a cup of tea as it cooled. It seems obvious. Heat moves, it spreads, it leaves a hot thing and enters a cold one, the way water runs downhill. Surely then, it is some kind of invisible liquid flowing from warm places to cool ones. That idea was reasonable, and careful people believed it for a very long time. And it was wrong. Heat is not a substance at all. When you finally learn what it really is, it turns out to be one of the most beautiful ideas in all of physics, and it is happening in you, everywhere in you, at every moment, in numbers too large to picture. Tonight, we are going to sit with all of it, gently. The parts that make clean sense, and the parts that still puzzle the people who study them. You don't need to follow every step. You don't need to hold anything in your head. If you drift off somewhere in the middle, that is completely fine. Your body will keep its warmth while you sleep, without any effort from you, the way it always has. The ideas will still be here in the morning. And so will you. So let's start where the story actually starts. Not with a laboratory, and not with a thermometer. Let's start with fire, because fire is where people first met heat as something to wonder about, and fire fooled them for thousands of years. Watch a fire for a while, in the dark, the way people have for as long as there have been people. It leaps and flickers. It seems alive. It seems to come out of the wood and rise up into the air and vanish. It gives off warmth and light, and then leaves nothing behind but ash. To the ancient eye, fire looked like a thing being released, some hidden substance escaping the wood and flying up. And so heat and fire got tangled together, and both were imagined as a kind of stuff. The ancient Greeks made it official. They taught that everything was made of 4 elements: earth, water, air, and fire. Fire was one of the basic building blocks of the world, as real and as material as water or stone. And that idea, fire as an element, a substance, lasted more than 2,000 years. Heat was not seen as a behavior of ordinary matter. It was seen as its own kind of thing, that came and went, that could be added to a body or taken away. When you warmed something, you were putting the fire stuff into it. When it cooled, the stuff left. It is a very natural way to think, and it set the stage for a more sophisticated version of the same mistake, one that would dominate science right up to the edge of the modern world. The idea that heat is an invisible fluid. It even had a name: caloric. The caloric theory was the serious, grown-up version of the fire element, and it was held by brilliant people. The idea was this: heat is a real, physical fluid, invisible and weightless, that fills the spaces inside and between the particles of matter. They called it caloric. When you heat something, caloric flows into it. When it cools, caloric flows out. A hot object simply contains more of this fluid than a cold one, and heat flows from hot to cold for the same reason water finds its level because the caloric spreads out from where there is a lot of it to where there is less. It was a lovely, tidy picture, and it explained a great deal. Think about how well it seemed to work. Why does a metal bar get longer when you heat it? Because you are pouring caloric into it, and all that extra fluid needs room, so the bar swells to hold it. Why does heat always flow from the hot cup to your cold hands, and never the other way? Because caloric, like any fluid, flows downhill from more to less. Why can you feel heat pass along a metal spoon left in a hot pot? Because the caloric is seeping through the metal, from the hot end to the cold. The theory even suggested why there might be a coldest possible state. If heat is a fluid, then the coldest anything could ever be is the state where all the caloric has been removed, where there is simply none left to take away. Empty of warmth. It was a coherent, useful, quantitative idea, and the greatest chemist of the age, Antoine Lavoisier, the man who did so much to build modern chemistry, put caloric right on his official list of the chemical elements, alongside oxygen and hydrogen. Heat, in the best science of the 1700s, was an element, a substance, a thing. And to study a substance, you have to measure it, which meant people needed a way to put numbers on hot and cold. This is where the thermometer comes in, and where a quiet but crucial distinction was born, one that trips people up even now, the distinction between heat and temperature. They are not the same thing, and keeping them apart is the beginning of really understanding either one. Early thermometers were simple. A thin tube with a liquid inside, usually mercury or colored alcohol, that swells and rises when warmed and shrinks and falls when cooled. The trick was agreeing on the marks. Where do you put the numbers? Two names ended up on the scales we still use. Daniel Fahrenheit, a German instrument maker working in the early 1700s, made superb mercury thermometers and fixed his scale using, among other points, the temperature of the human body and the freezing of a certain salty mixture. His scale is the one that puts water's freezing at 32 and its boiling at 212, and it is still used in a few countries. A little later, a Swedish astronomer named Anders Celsius proposed a cleaner scale, built around water itself, with 0 at freezing and 100 at boiling, divided into a neat 100 steps. Most of the world uses his scale now. But notice what a thermometer actually measures. It measures temperature, how hot something is, the intensity of the warmth. It does not measure heat, the total amount of warmth energy in a thing. And those are genuinely different. A single spark from a fire can be far hotter, higher in temperature, than a whole warm bath. But the bath holds vastly more heat, far more total warmth, enough to raise your whole body, while the spark, for all its fierce temperature, could not warm you at all. Temperature is how hot. Heat is how much. Holding those two apart was the first step towards seeing that heat was not quite the simple fluid it seemed, and the man who measured that difference most carefully was a mild Scottish professor named Joseph Black. Joseph Black taught in Glasgow and later Edinburgh in the 1700s, and he was a careful, patient man who liked to measure things precisely. And in his measuring, he found two hidden things about heat that nobody had properly noticed, and both of them are quietly strange, and both are still taught today. The first is called latent heat, and you can see it in a glass of ice water. Take some ice, well below freezing, and warm it steadily. The temperature climbs, as you would expect, right up until the ice reaches its melting point. And then something odd happens. As the ice actually melts, the temperature stops rising. It sits there, stuck at the melting point, even though you are still pouring heat in. The whole time the ice is turning to water, All that heat is going somewhere, but it is not making anything hotter. Only once the last of the ice has melted does the temperature start to climb again. Black realized that a large amount of heat gets swallowed up, hidden in the very act of melting, without changing the temperature at all. He called it latent heat, from the Latin for hidden, because it seemed to vanish into the ice, doing the work of melting rather than the work of warming. The same thing happens, even more dramatically, when water boils. A pot of water sits at its boiling point and stays there, no matter how hard you heat it, while huge amounts of heat pour in to turn the water into steam. The heat is hiding in the change from liquid to gas. This is why steam can scald so badly, far worse than the same weight of boiling water, because it carries all that hidden heat with it and dumps it onto your skin when it condenses back. Latent heat is why sweat cools you, because your body's warmth is swallowed up, turning that sweat into vapor. Black had found heat doing something invisible, hiding inside a change of state, and it was a real and measurable amount. His second discovery was that different substances soak up heat differently. Take the same amount of heat and put it into equal weights of water and of iron, and they do not warm by the same amount. The iron heats up quickly. The water is stubborn and warms only slowly, swallowing a great deal of heat for every degree it climbs. Black called this the specific heat, the particular appetite each substance has for warmth. Water, it turns out, has an unusually large appetite. It takes a lot of heat to warm it, and it gives up a lot as it cools, which is why the ocean is so slow to change temperature, and why a warm bath stays warm, and why water is so good at carrying heat around. These were not just curiosities. They were the first precise, quantitative facts about heat, real numbers, and they let people start to do genuine bookkeeping with warmth, adding it up, tracking where it went. And oddly, none of this yet broke the caloric theory. You could still imagine the hidden heat as caloric fluid, tucked into the melting ice. Black himself mostly stayed within the fluid picture. It took a soldier, an adventurer, and a man of enormous vanity to notice the thing that finally cracked it open. And he noticed it while making weapons. His name, by the end of his colorful life, was Count Rumford, but he was born Benjamin Thompson in Massachusetts in 1753. He was a spy, a soldier, an inventor, and a relentless social climber. He backed the losing side in the American Revolution, fled to Europe, and eventually took service with the ruler of Bavaria, where he reorganized the army, fed the poor, and was made a count of the Holy Roman Empire. He chose the name Rumford after the old name of a town in New Hampshire. He was, by most accounts, arrogant and difficult and hungry for recognition, and he had a genuinely sharp eye. In the 1790s, part of his job in Munich was overseeing the making of cannon, and cannon in those days were bored out of solid blocks of metal, with a great drill grinding away inside the barrel to hollow it. And standing in that workshop, watching the boring, Rumford noticed something that troubled him. The metal got hot, ferociously hot. The friction of the drilling produced so much heat that the workers cooled the cannon with water, and Rumford saw that the water could actually be boiled by the heat of the boring, over and over, as long as the horses kept turning the drill. And he asked a simple, deadly question of the caloric theory. Where is all this heat coming from? If heat is a fluid, a substance stored in the metal, then boring the cannon must be squeezing the caloric out of it, like water from a sponge. But a sponge runs dry. If the heat were a fluid being pressed out of the metal, it should eventually run out. The metal should give up its store of caloric and then go cold. And it never did. As long as the drill kept turning, the heat kept coming without end, apparently forever. You could boil the water again and again. There seemed to be no limit at all. Rumford saw what that meant, and it was radical. A limitless supply cannot be a substance drained from the metal, because any substance would run out. The heat was not being released from the iron. It was being created, freshly, continuously, by the motion of the drill, by work, by friction. And if heat could be made without limit simply by grinding one thing against another, then heat was not a stored fluid at all. It had to be, he suggested, a kind of motion. He wrote that anything which could be produced without limit, the way this heat could, simply could not be a material substance, and that it seemed impossible to imagine heat as anything other than motion. It was a beautiful piece of reasoning, and it landed, in the year 1798, like a quiet crack running through the foundation of the caloric theory. Rumford could not prove exactly what was moving, or how. He did not have the atoms. But he had shown, in a cannon workshop, that heat could be conjured endlessly out of mechanical work, and that a fluid theory could not survive it. The caloric began, slowly, to leak away. It took another 50 years, and a very different kind of man, to finish the job and put a hard number on it. A brewer's son, in England, with a private laboratory and an almost obsessive love of precise measurement. But before we get to the brewer's son, there is a young Frenchman we have to meet, because he built the deepest idea about heat before anyone even knew what heat was, and he did it while still believing in caloric, and his results survived anyway. His name was Carnot, and his story is a quiet tragedy. He was the son of one of Napoleon's most important officials, and he grew up in the shadow of the great steam engines that were beginning to change the world. It is worth pausing on those engines, because they are where the science of heat was really born, not in a laboratory, but in the noise and smoke of industry. The story goes back to a practical problem. Coal mines flooded. Water seeped in and had to be pumped out, and pumping it by hand or by horse was slow and dear. So people built machines to do it with fire. The first that truly worked was made by an English ironmonger named Thomas Newcomen, around 1712. It used the heat of burning coal to boil water into steam, and then cooled the steam to make it collapse, and the collapse pulled a great beam up and down, working a pump. It was enormous, and it was clumsy, and it wasted almost all of its heat. But it worked, and it drained the mines, and it was the first engine to turn the warmth of fire into steady, useful work. Then came a Scottish instrument maker named James Watt in the 1760s, who was asked to repair a small model of Newcomen's engine and grew fascinated by how wasteful it was. The engine heated its cylinder and then cooled it, over and over, throwing away heat with every stroke. Watt saw the flaw and had an idea that changed the world. He added a separate chamber to cool the steam so the main cylinder could stay hot all the time. Suddenly, the engine used far less coal for the same work. It was efficient enough to be used not just to pump mines, but to drive machines, factories, mills, and eventually wheels on rails. Watt's engine, more than almost anything, powered the Industrial Revolution, the great transformation that pulled the world from farms and handwork into factories and machines. The unit of power we still use, the watt, the one printed on every light bulb, carries his name. But here is the thing about all these engines. They worked, and nobody understood why they worked, or how well they could ever be made to work. Steam engines were everywhere, pumping water out of mines, driving factories, hauling loads, and yet the science of them did not exist. Engineers improved them by trial and error, tinkering, guessing. Carnot wanted to understand them properly. He wanted to know the deepest question: what is the most work you could ever possibly get out of heat? Is there a limit? And if there is, what sets it? In 1824, in a short book, he answered it, and the answer was profound. Carnot imagined a perfect engine, an idealized one with no friction and no waste, and he reasoned about how heat could be turned into useful work. And he saw that an engine does not work by using up heat the way a fire uses up wood. An engine works by letting heat flow from something hot to something cold, and catching some of that flow and turning it into motion along the way. Like a water wheel, which does not consume the water, but takes energy from it as it falls from a high place to a low one. An engine takes its work from heat as it falls from a high temperature to a low one. And that gave him his stunning conclusion. The most work you can ever get depends only on the difference in temperature between the hot source and the cold sink. The bigger the gap between hot and cold, the more work is possible. And no engine, however cleverly built, can ever do better than his perfect ideal. There is a hard ceiling, set by nature, on how much of the heat can become work. Some of it must always be dumped, wasted, into the cold. This was the true beginning of the science we now call thermodynamics, the study of heat and work and energy, and it is remarkable for two reasons. First, because that limit Carnot found is real and absolute, and it still governs every engine, every power plant, every turbine on Earth today, from a car to a rocket to the great generators we met in the story of electricity. And second, because Carnot got the right answer using the wrong theory. He still thought heat was caloric, a fluid falling from hot to cold like water down a wheel. The picture was wrong, but the reasoning about limits was so deep that it survived the death of the theory it was born in. Carnot himself began to doubt caloric near the end, and in his private notes he came remarkably close to the modern view, writing that heat was probably motion. But he never published those doubts. He died in 1832, at only 36, in a cholera epidemic. And because of the fear of cholera, many of his belongings and papers were burned with him. We will never know how much of the answer died in that fire. A young man saw further than anyone into the nature of heat engines, kept his deepest thoughts in a private notebook, and most of it went into the ground with him at 36. Now, at last, the brewer's son. His name was James Prescott Joule, and he was born in 1818 near Manchester, in England, into a family that owned a prosperous brewery. He was not a professor. He was a businessman who did science in his spare time and at his own expense, and he had an almost fanatical devotion to careful measurement, the kind of patience that borders on obsession. Running a brewery is a business of precise temperatures, and perhaps that is where his fascination began. What Joule set out to prove, across the 1840s, was the thing Rumford had only gestured at, that heat and mechanical work are two forms of the same thing, and that there is an exact rate of exchange between them, that you can convert a specific amount of work into a specific amount of heat, always the same amount, every time. His most famous experiment is beautifully simple. He took an insulated barrel of water, and inside it he placed a paddle wheel connected by strings and pulleys to a pair of heavy weights. As the weights slowly fell under gravity, they turned the paddle, and the paddle churned the water. The falling weights did a measurable amount of mechanical work he could calculate exactly from how heavy they were and how far they fell. And the churning paddle warmed the water, very slightly, by an amount he could measure with a sensitive thermometer. The water was not touching any fire. No caloric was flowing in from anywhere. The only thing happening was motion, stirring, work being done on the water. And the water got warmer. Joule did this again and again with fanatical care, and he found that a given amount of work always produced the same fixed amount of heat. He had measured the exchange rate between work and warmth, a number now called the mechanical equivalent of heat. Think about what that means. It means heat is not a separate substance you add to things. It means heat is just another form of energy, the same energy as a falling weight, the same energy as a moving object, only in a different guise. Do work, stir, rub, churn, and you can turn motion into warmth at a fixed and reliable rate, with nothing flowing in from outside. Caloric was finished. There was no fluid. There was only energy, changing its form from the motion of a weight to the warmth of water. There is a charming story that Joule was so devoted to this idea that on his honeymoon in the Alps, he tried to measure the temperature of the water at the top and bottom of a waterfall, expecting the water to be very slightly warmer at the bottom, warmed by the work of its own fall. The story is probably embroidered, but it captures the man perfectly, a person who looked at a waterfall and saw energy quietly turning into heat. At first, almost nobody took Joule seriously. He was an amateur, a brewer, reading papers to unimpressed audiences. It took the support of a young and respected physicist, William Thomson, later known as Lord Kelvin, who slowly realized the brewer was right to bring Joule's work into the heart of science. And once it was accepted, it opened straight into one of the grandest ideas we have ever had. That energy, in all its forms, is never created and never destroyed. It only changes shape. This idea is called the conservation of energy. It is one of the deepest laws we know, and like the discovery of the expansion of the universe, it did not belong to one person. It arrived in several minds at once. A German physician named Julius Robert von Meyer got there around the same time as Joule, from a completely different direction. He was a ship's doctor. On a voyage to the tropics, he noticed that the blood of sailors looked different in hot climates. He reasoned his way from that, remarkably, to the idea that heat and work and the energy in food were all the same currency, all convertible, all conserved. He published it. Almost no one listened. He was a doctor, not a physicist, and his life was hard. He lost children. He was mocked. He was even confined for a time in an asylum. He nearly did not survive being ignored. A little later, a great German scientist named Hermann von Helmholtz laid the idea out with full mathematical force, and slowly it became clear and undeniable. Energy is never made and never lost. It only changes form. This is now called the first law of thermodynamics. Sit with how large it is. The chemical energy in your dinner becomes the motion of your muscles, and the warmth of your body, and the electrical signals in your nerves. A falling weight becomes heat in Joule's water. Sunlight becomes sugar in a leaf. Coal becomes steam, becomes spinning metal, becomes electricity, becomes light. At every step, the form changes, and the total stays exactly the same. Nothing is ever gained. Nothing is ever truly spent. The universe has a fixed amount of energy, shuffled endlessly from one shape to another, and heat is simply one of those shapes. Not a substance, a form of energy. The same energy as everything else. So heat is energy. But energy of what? That was the question left standing. Rumford had said heat was motion. But the motion of what? What is actually moving when a thing is hot? The answer had been whispered for a long time by a few people ahead of their time, and it is the heart of this whole night. Heat is the motion of atoms. When something is hot, its atoms and molecules are jiggling, trembling, rushing about. When it is cold, they move slowly. That is all heat is. It is not a fluid poured into matter. It is the matter itself, in motion, at a scale far too small to see. Let that picture settle in. because it is genuinely one of the loveliest ideas in physics, and it is happening in you right now. Everything is made of atoms. In a solid, like the bed frame or your own bones, the atoms are locked in place, but they are not still. They quiver. They vibrate around their spots, jittering back and forth, faster when warm, slower when cold. In a liquid, like the water in you, the atoms and molecules slide and tumble over each other, jostling, bumping, in constant restless motion. In a gas, like the air above your face, the molecules fly free, whizzing about at great speed, crashing into each other and into everything else, millions of collisions every instant. And the hotter the thing, the faster all this motion. Heat is that motion. Temperature is a measure of how vigorous it is. To warm something is simply to make its atoms move faster. To cool it is to let them slow down. The idea is old. A Swiss mathematician named Daniel Bernoulli worked out much of it back in the 1730s, imagining a gas as a swarm of tiny particles banging on the walls of their container and showing that their banging would produce exactly the pressure we measure. He was decades ahead of everyone. He was mostly ignored because caloric ruled. But in the 1850s and 60s, once heat was known to be energy, the idea came roaring back, and it was built into a full and rigorous theory called the kinetic theory of heat, the theory of heat as motion. The German physicist Rudolf Clausius did much of the work, and it explained everything, cleanly, without any fluid at all. Why does a gas push outward on its container? Because its flying molecules are drumming on the walls, countless tiny impacts adding up to a steady pressure. Why does heat flow from hot to cold? Because fast jiggling atoms, bumping into slow ones, share their motion, speeding up the slow ones and slowing themselves, until the motion is spread evenly. The warmth spreads because the jostling spreads, atom to atom, like a whisper passed through a crowd. Why does a metal spoon carry heat so well? Because its atoms and loose electrons pass the jiggling along quickly. Why does rubbing your hands warm them? Because you are pushing their atoms into faster motion by force, exactly as Rumford's drill did to the cannon. Every single thing the caloric fluid was supposed to explain, the motion of atoms explained better, and with no invisible substance required. Heat had been hiding in plain sight. It was just matter, shivering. And this picture explains something you see every day, the way a single substance can wear such different faces. Water is the easy example. It can be hard ice, or flowing liquid, or invisible steam. Same stuff, same molecules, every time. The only difference is how much they are moving. In ice, the molecules are cold and slow. They lock into a rigid pattern, held in place, barely trembling. That is a solid. Add heat. The molecules move faster. Soon they are jostling too hard to stay locked, and the pattern breaks, and they begin to slide over one another. The ice melts. That is a liquid. Add more heat. They move faster still, until some of them are moving fast enough to break free of each other entirely and fly off alone. The water boils away into vapor. That is a gas. Solid, liquid, gas. Three faces of one substance, and the only thing that changes is the speed of the trembling. This is what was really happening in Joseph Black's melting ice all those movements ago, with its hidden heat. When ice melts, the heat you pour in is not speeding the molecules up. It is being spent breaking the bonds that hold them in their rigid pattern, prying them loose from their fixed places. That is why the temperature holds steady while the ice melts. The heat is doing the work of unlocking, not the work of warming. Only once the lattice is broken and the molecules can flow does the temperature climb again. The hidden heat was the price of freeing the atoms from their frozen order. Boiling is the same. at a higher rung, the price of freeing them from each other altogether. And there are more states than the familiar three at the far ends of the scale. Go hotter than a gas, hot enough, and the atoms themselves begin to break, their electrons torn away, and you get a glowing soup of charged particles called a plasma. It is the fourth state of matter, and though it is rare on the cool surface of the earth, it is actually the most common state in the universe, because it is what the stars are made of. Every star is a vast ball of plasma, matter too hot to hold itself together as ordinary atoms. The sun is plasma. Lightning is a brief thread of plasma. Most of the visible universe is this fourth, fierce, glowing state, and it exists because of heat, because of motion too violent for atoms to survive. And at the very other end, in the deepest cold, near absolute zero, matter can do something stranger still. Chill certain atoms to within a breath of the absolute bottom, and they can slow so completely, and their motion grow so faint, that they stop behaving as separate atoms at all. They merge, in a sense, into a single shared state, all of them acting as one, a kind of matter that has no everyday name and no everyday behavior. It is called a Bose-Einstein condensate, predicted by Einstein and an Indian physicist named Satyendra Nath Bose long before anyone could make one, and finally created in a laboratory in 1995 in a cloud of atoms cooled to less than a millionth of a degree above absolute zero. It is one of the coldest, quietest things that has ever existed. So heat, or the lack of it, decides everything about what matter is. Take it away, and atoms freeze, and then merge into a silent whole. Pour it in, and they loosen, and flow, and fly apart, and finally shatter into the glowing plasma of the stars. All of it, from the coldest quiet to the fiercest fire, is one thing. It is matter, moving at every possible speed. So if heat is the motion of atoms, then temperature, the thing your thermometer reads, is a measure of how fast, on average, those atoms are moving. More precisely, temperature reflects the average energy of motion of the particles in a thing. Hot means the atoms are, on average, moving fast and carrying a lot of energy of motion. Cold means they are, on average, moving slowly. That little phrase, on average, matters, and it is where the great Scottish physicist James Clerk Maxwell comes back into our story, the same Maxwell who turned electricity into light. Because the atoms in a warm gas are not all moving at the same speed. They are all moving at wildly different speeds, a whole spread of them, and they are constantly trading speed as they collide. Maxwell worked out, in the 1860s, the shape of that spread. In any warm gas, a few molecules are barely moving at any instant, and a few are racing along far faster than average, and most are somewhere in the middle, clustered around a typical speed. This spread is now called the Maxwell distribution, and it was one of the first times anyone described nature using pure statistics, using probability, rather than tracking each thing individually. You cannot follow every molecule. There are far too many. But you can describe the crowd, the pattern of the whole swarm, and that turns out to be enough. Temperature is a fact about the crowd, not about any single atom. A single atom does not really have a temperature. Temperature is what emerges when countless atoms share their motion and settle into that bell-shaped spread of speeds. And the speeds are astonishing. This is one of those quiet facts that should make you smile as you lie there. The air molecules just above your face, in this ordinary room, at this ordinary temperature, are not drifting gently. They are flying. On average, they are moving at something like 1,000 miles an hour, faster than a jet, faster than sound. They are so light and so numerous that you feel none of it. Only a soft pressure and a mild warmth. But the air in your room is a storm of tiny particles each one hurtling along at the speed of a rifle bullet, each one crashing into others billions of times every second, ricocheting, never resting. The stillness of a quiet room is an illusion of scale. Down among the molecules, it is pure chaos, a furious blur of motion, and that furious motion is exactly what you feel, gently, as the warmth of the air. When you warm the room by a few degrees, you are speeding that swarm up a little more. When it cools, the swarm slows. The temperature is just the tempo of an unimaginable dance. Now we come to the strangest and deepest thing about heat, the thing that separates it from almost everything else in physics, and it hides inside a simple, everyday fact. Heat only ever flows one way. It flows from hot to cold, never on its own, from cold to hot. A hot cup of tea always cools down to room temperature. It never, ever spontaneously grows hotter by drawing warmth out of the cool room. Drop an ice cube into warm water, and the ice melts and the water cools until everything is the same lukewarm temperature. You will wait forever to see the reverse, the water spontaneously freezing part of itself back into ice while the rest boils. It simply does not happen. And this is genuinely strange, because nothing in the basic laws of motion forbids it. Here is the puzzle, gently. The atoms are just bouncing around, and the laws that govern each little collision work perfectly well in reverse. If you filmed two atoms colliding and played it backward, it would look completely normal, a perfectly legal collision. So why, when you have countless atoms together, does the whole thing suddenly have a direction? Why does the film of a cup of tea cooling look obviously right, while the film run backward, the tea gathering warmth from the room and heating up, looks absurd and impossible? Where does that one-way street come from, if every single step along it is reversible? This is one of the great questions in physics, and the answer is one of the most beautiful ideas we have. It is called entropy, and the rule it obeys is called the second law of thermodynamics. The answer is about counting, and about how overwhelmingly likely the spread-out state is. Think of it this way. When heat is concentrated in the hot tea, all that fast motion is gathered in one small place, and the cool room is separate. That is a very special, very orderly arrangement, like all the fast molecules sorted onto one side. There are very few ways to arrange the atoms so that all the fast ones sit in the cup, but there are unimaginably many ways to arrange them so that the fast motion is spread out evenly, shared among the tea and the room together. So as the atoms bump and jostle and trade their motion at random, they simply stumble, overwhelmingly likely, from the rare orderly arrangement into one of the countless spread-out ones. Not because any law pushes them, just because the spread-out states are so many more that random jostling almost always lands there. Heat spreads out for the same reason a shuffled deck comes out disordered. There are just far more ways to be mixed than to be sorted. Entropy is the name for that spreading, a measure of how spread out and shared the energy is, how many ways the atoms could be arranged and still look the same. And the second law says that in any closed system, entropy tends to increase. Things spread out. Order gently dissolves into disorder. Heat flows from hot to cold. Differences even themselves out, not because they must in any single collision, but because the evened out state is so overwhelmingly more likely that the universe, left to itself, drifts into it, always, with the patience of enormous numbers. This is the one law of physics that knows the difference between past and future. It is why the tea cools and never uncools. It is, many think, the very source of the direction of time itself, the reason tomorrow feels different from yesterday. That is a thread for another night, a whole story of its own. But it begins here, in the simple fact that heat spreads and never gathers, because spreading is what the odds demand. And once you see entropy this way, as the quiet arithmetic of what is likely, you start to notice it everywhere, in the smallest ordinary things. Watch a drop of ink fall into a glass of clear water. It swirls and unfurls and slowly spreads until the whole glass is evenly, faintly colored. And it never gathers back. You will never see a glass of pale gray water spontaneously pull its ink back into a single dark drop. Why? Not because any law forbids it. Only because there are countless ways for the ink to be spread through the water, and vanishingly few ways for it to be gathered in one drop. So the spreading happens, and the gathering does not, for the same reason heat spreads. The odds are simply overwhelming. It is the same when perfume drifts across a room until you can smell it in the corner. The same when a sandcastle crumbles into a smooth beach and never assembles itself from the waves. The same when a cup shatters on the floor and never leaps back together whole. The same when you stir cream into coffee and the swirl fades into an even tan, and no amount of stirring brings the white back. All of these are entropy, the drift from the special and ordered toward the common and mixed. All of them are one way. You have never seen any of them run backward, and you never will. Not because the reverse is impossible in principle, but because it is so absurdly unlikely that the whole age of the universe would not be long enough to wait for it. This is the strange gift of large numbers. Each tiny piece is reversible, and the whole is not, and the difference is only counting. There is a gentle thought in that, for lying in the dark. So much of what makes the world feel the way it does, the way a smell fades, the way a room cools, the way things worn and broken do not mend themselves, the way the past is fixed and the future is open, comes down to this one soft fact. There are more ways to be spread out than gathered. The universe is not being pushed anywhere. It is only wandering, at random, into the states that are most numerous, the way a wandering walker in a wide field ends up, almost always, somewhere in the vast middle, rather than back in the small corner where it started. Everything settles, because settled is simply where most of the room is. There is a puzzle tucked inside all of this that is worth pausing on, because it leads somewhere lovely. If heat is the jiggling of atoms, passed along by atoms bumping into atoms, then how does the warmth of the sun reach us at all? Between the sun and the earth lies 93 million miles of empty space, almost perfect emptiness, with almost no atoms in it to pass the jiggling along. And yet the sun warms your face on a clear day. The heat crosses the void. So heat cannot only travel by atoms bumping. There must be another way. And there is. There are, in fact, 3 ways heat moves, and the third one is the answer, and it ties this whole story back to light. The first way is the one we have been describing. It is called conduction, heat passing directly through a material as its jiggling atoms nudge their neighbors. This is how a spoon warms in a hot pot, how the cold of the floor creeps into your feet, how a mug warms your hands. Atom to atom, motion handed along, touching all the way. The second way is called convection, and it happens in liquids and gases that can flow. Warm air is lighter and rises, cool air sinks, and so the warmth is carried bodily from place to place by the moving fluid itself. It is why the warmth of a heater fills a room, why the water at the top of a pot boils last, why weather happens at all. The warm stuff physically moves, carrying its heat with it. But the third way needs no atoms at all, and it is how the sun reaches you. It is called radiation, and it is simply this. Anything warm gives off light. Not always light you can see, but light all the same. The electromagnetic waves we met in the story of electricity. A warm object, because its charged particles are jiggling, sends out that jiggling as electromagnetic waves, radiating its heat away as light, which can cross empty space at the speed of light and warm whatever it lands on. The sun is fiercely hot, so it pours out a flood of this radiation, much of it visible, and it crosses the empty void and lands on you and sets your own atoms jiggling faster, and you feel it as warmth on your skin. No atoms in between are needed. The heat travels as light and becomes heat again when it arrives. And here is the gentle, astonishing part. You are doing it too, right now. You are warm, so you are glowing. Not invisible light, but an infrared, a color of light just past the red end of what your eyes can see. Your body is pouring out heat as invisible light, steadily in every direction, into the dark room. A camera built to see infrared would show you shining, bright and warm, the shape of your body drawn in light against the cooler room. Every warm thing glows this way. The bed glows faintly. A sleeping animal glows. A cup of tea glows and slowly dims as it cools. The whole world is quietly luminous with its own heat, trading warmth back and forth as invisible light, and you are one of the warm, glowing things in it, giving off a soft, steady light you have never once seen. That is heat, leaving you gently, as light, all night long. Now, if heat is motion, a natural question arrives, and it is one we will only touch tonight, because it deserves its own evening. If warming a thing means speeding its atoms up, and cooling it means slowing them down, then how cold can something get? Is there a bottom? A slowest the atoms can go? And the answer is yes. There is a coldest possible temperature, a floor beneath which nothing can fall, and it comes from exactly this picture of heat as motion. If you cool a thing more and more, its atoms move less and less. Keep going, and eventually they slow to the barest minimum motion allowed. At that point, you cannot take any more heat out, because there is no more motion to remove. That is the coldest anything can ever be. It is called absolute zero. Absolute zero sits at about minus 273 degrees on the Celsius scale, and it is so important that physicists built a whole temperature scale starting from it. It is called the Kelvin scale, named for that same William Thomson, Lord Kelvin, who championed Joule. On the Kelvin scale, zero is absolute zero, the true bottom, the coldest there is, where motion all but stops. Room temperature is around 300 Kelvin. Nothing in the universe is colder than 0 Kelvin, because there is no such thing as less motion than none. It is not merely very cold. It is the end of cold, the floor of the whole scale of temperature. And there is something strange and beautiful about that floor, which is that you can never actually reach it. You can get closer and closer, unimaginably close, colder than the depths of empty space, colder than anywhere in nature. Laboratories have chilled tiny clouds of atoms to within a hair of absolute zero, to billionths of a degree above it. But that final step, to zero itself, to perfect stillness, seems to be forbidden, no matter how clever you are. Getting there would take infinite effort, an endless number of steps, each one harder than the last. Why that is, why the universe hangs a floor beneath all temperature and then makes it impossible ever quite to touch, is a lovely story in its own right, and one for another night. For now, it is enough to know that heat has a bottom, a place where the trembling nearly ceases, and that we can approach it but never arrive. Even the stillest thing in the universe is still, very faintly, moving. The person who saw most deeply into all of this, into heat and entropy, and the counting of arrangements, was an Austrian physicist named Ludwig Boltzmann, and his story is the quiet, sad heart of this whole night. Boltzmann, in the 1870s, took the idea of heat as motion and built it into a complete and rigorous science, the field we now call statistical mechanics. He understood that the behavior of heat, of temperature, of entropy, all of it, comes from the statistics of countless tiny particles, from the overwhelming force of large numbers. He gave entropy its deep meaning. He showed, with a single beautiful equation, that the entropy of a state is a measure of how many microscopic arrangements of atoms would look the same from the outside. More arrangements, more entropy. The spread out states have vastly more arrangements, so entropy climbs, so heat spreads. It all followed from counting. That equation, relating entropy to the number of arrangements, is one of the most important in all of physics. It is carved on his gravestone in Vienna, in the old notation, a short line of symbols that captures why time has a direction, and why heat flows, and why the universe drifts towards sameness. It is a strange and moving thing to put an equation on a grave, but there is a darkness behind it. Boltzmann built his entire life's work on the reality of atoms, on the idea that matter is made of tiny particles whose motion is heat. And in his lifetime, atoms were not accepted. Many of the most respected scientists of his day did not believe atoms were real. They thought them a convenient fiction, a calculating trick, and they attacked Boltzmann's work, sometimes fiercely, for resting on things no one had ever seen. He fought for it for years, against the tide, defending the reality of the invisible particles that his whole science required. He suffered from deep swings of mood, long darknesses, and the constant opposition wore him down. In 1906, on a summer holiday, while his wife and daughter were out swimming, Ludwig Boltzmann took his own life. He was 62, and the terrible, tender irony is that he died just as the tide was turning. Only a year or two earlier, a young Albert Einstein had published work that would soon prove atoms were real beyond any doubt by explaining the tiny jittering dance of pollen grains in water as the result of countless invisible molecules bumping them. Within a few years of Boltzmann's death, essentially every physicist accepted the atoms he had staked his life on. He was right. He was completely right. He simply did not live to see himself vindicated. When you hear that heat is the motion of atoms, that temperature is their average energy, that entropy is the counting of their arrangements, you are hearing the work of a man who believed it when it cost him everything and who did not quite make it to the morning. It is worth pausing on that proof, the one that came too late for Boltzmann, because it is such a quiet and beautiful piece of seeing. For a long time, the trouble with atoms was simple. Nobody had ever seen one. They were far too small. So how could you ever prove they were real, and not just a convenient story? The answer had been sitting under a microscope since 1827, unexplained. A botanist named Robert Brown had noticed that tiny grains, pollen and dust, suspended in water, jittered and trembled and wandered about, ceaselessly, for no reason anyone could see. They never stopped. This restless dance was named Brownian motion, after him, and for nearly 80 years it was a curiosity with no explanation. Then, in 1905, the young Einstein worked it out. The little grains were being bombarded, he said, on every side, by the water molecules, far too small to see, crashing into them from all directions. Most of the time the bumps roughly cancel, but now and then, by chance, a few more strike from one side than the other, and the grain lurches. The trembling of the visible grain was the invisible molecules, made visible at one remove, betraying themselves by the way they jostled something big enough to watch. Einstein worked out the mathematics of that dance in detail, and a French physicist named Jean Perrin carefully measured it, and it matched exactly. You could not see the atoms, but you could see the twitch of what they hit, and that was enough. After that, the reality of atoms was beyond serious doubt. The invisible particles whose motion is heat had finally left a fingerprint anyone could check. And with atoms secure, the whole science of heat stood on firm ground, and it can be gathered into a few simple laws which are worth hearing plainly, because for all their depth, they are almost humble. There is a playful way people sometimes state the laws of thermodynamics, and it holds a lot of truth. The first law, that energy is conserved, says you cannot win. You can never get more energy out than you put in, because the total never changes. The second law, that entropy increases, says you cannot even break even, because some energy always spreads away, wasted as heat, every time, and you can never get it all back to do work. And there is a third law, which says you cannot quit the game either, because you can never reach absolute zero, never get all the way down to perfect stillness and rest. You cannot win. You cannot break even. You cannot get out of the game. It sounds bleak, put that way, but it is really just the honest shape of things, the rules every engine and every living body and every star must play by, written in the spreading of heat. It is worth taking a moment, before we turn for home, to feel the sheer range of temperature in the universe, from the gentlest cold to the most violent heat, because it puts the warmth of your own body in a kind of perspective. Your body sits at a very particular, very narrow temperature, around 37 degrees on the Celsius scale, 310 on the Kelvin scale, and you can only survive within a few degrees of it. Life is a delicate thing, tuned to a thin band of warmth, but the universe ranges far, far beyond that band, in both directions. Go colder first. The air around you is warmer than the night outside, which is warmer than the poles, which are warmer than the coldest natural place we know. But all of that is balmy compared to deep space. Far from any star, the emptiness between the galaxies is not truly at absolute zero, because the whole universe is filled with a very faint warmth, the afterglow of its own beginning, sitting at just under 3 degrees above absolute zero. That faint glow, the cosmic microwave background, sets the temperature of the empty cosmos, cold almost beyond imagining, but not quite zero. And colder still, colder than anywhere in all of nature, are the tiny clouds of atoms that physicists cool in their laboratories, chilled to billionths of a degree above the absolute bottom, the coldest things that have ever existed anywhere, made by human hands. Now go the other way, into heat. The surface of the sun is around 5,000 or 6,000 degrees, hot enough to vaporize anything, but that is its cool outer skin. Its core, where its energy is made, is around 15 million degrees, and the sun is a mild star. When a great star dies and explodes, a supernova, it briefly reaches billions of degrees. Hotter still, in the great machines where we smash particles together, we have recreated for a fraction of an instant the heat of the newborn universe, trillions of degrees, so hot that ordinary matter melts into a soup of its most basic pieces, a state called a quark-gluon plasma, the hottest thing ever made on Earth. And hottest of all was the universe itself, in its very first moment, hotter than any number that means much to us. From that first fire, everything has been cooling, for nearly 14 billion years, spreading its heat outward, drifting toward the faint cold glow that now fills the dark between the stars. And you, lying here, are a small warm pocket in that long cooling, holding your thin band of life-giving warmth for a little while against the vast cold that surrounds it. It is worth knowing why the earth is warm enough to hold you at all, because it too comes down to heat and light. The sun warms our world with its radiation. The ground soaks up that warmth by day. And then the earth, being warm, glows too, giving off its own heat as invisible infrared light, trying to send it back out to space. If that were the whole story, the earth would be a frozen ball. The warmth would arrive and leave, and the surface would sit far below freezing. But there is a blanket. Our atmosphere holds certain gases, water vapor and carbon dioxide chief among them, and these gases let the sun's light in easily, but they catch some of the Earth's outgoing heat on its way back out. They absorb it and radiate it back down and warm the surface further. This is the greenhouse effect, and it is not a villain. It is the reason our world is livable. Without it, the Earth would be far too cold for anything like you. You can see the same thing, run to extremes, on our neighboring worlds. The moon has no air, no blanket at all, and so it swings between scorching heat in the sun and brutal cold in the shade, with nothing to hold the warmth. And Venus, our sister planet, has a thick, choking atmosphere heavy with carbon dioxide, a blanket far too heavy. It traps so much heat that its surface is hotter than an oven, hot enough to melt lead, hotter even than the planet closest to the sun. A world can be warmed too little or too much, all depending on the thin veil of gas around it. Our own Earth sits, for now, in a gentle balance, its blanket just heavy enough to keep the warmth that life needs, and no heavier. It is a delicate thing, that balance, and it is the reason the night around you, cold as it may feel, is not the true cold of space, but a mild and survivable cool, held soft by the air. There is a question hiding in the second law that touches you very directly, and it is worth sitting with gently. If everything drifts toward disorder, if entropy always climbs, if heat always spreads out and evens away, then how does a living thing exist at all? You are extraordinarily ordered. Your body is an intricate arrangement, atom upon atom, cell upon cell, held in a precise and delicate structure. A living thing is one of the least spread out, most orderly arrangements of matter there is. So how do you keep it up? How does life build and hold such order in a universe whose deepest law is that order dissolves? The answer is beautiful, and it is honest about the cost. Life does not break the second law, it pays it. A living thing keeps itself ordered by feeding on energy and giving off heat, by making a great deal more disorder around itself than the order it holds inside. You eat food, which is concentrated, ordered energy, gathered ultimately from the sun. You use it to maintain your own delicate structure, and you give off heat, constantly, warming the room, spilling disorder into the world around you. The order inside you is real, but it is bought at every moment by spreading more disorder outside you. The books balance. Entropy still climbs, for the universe as a whole. You are a small eddy of order in a river that flows, overall, towards spreading out. You hold your shape by never standing still, by always taking in energy and passing warmth along. The physicist Erwin Schrödinger wrote about this in a small and lovely book, asking what life is from the point of view of physics. He said that a living thing feeds on order, drinks in order from its surroundings, to hold back its own drift toward disorder, for as long as it lives. And that is exactly what the warmth pouring off your body is. It is the price of being alive, the disorder you shed so that you can stay ordered inside. The sun sends its concentrated energy to the earth. Plants catch it and build order, sugars and structures. You eat that order and burn it, and build yourself and give off heat. And that heat spreads out into the room, into the night, into the sky, and eventually radiates away into cold space, a little more spread out than when it began. Life is a flow, not a thing. It is warmth passing through, briefly held in a shape that thinks. When it stops, when the flow ends, the order lets go, and the atoms slowly return to the spreading. That is what it means to be a warm, living thing in a universe that tends toward cold. Now, people are clever, and a rule that says heat only flows one way is exactly the kind of rule someone will try to cheat. Maxwell himself, the same man again, dreamed up the most famous attempt as a kind of playful puzzle back in 1867. It is called Maxwell's Demon. Imagine a box of gas, all at one even temperature, the molecules flying about at their usual spread of speeds, some fast, some slow. Now imagine a tiny door in the middle of the box, and a tiny intelligent being, a little demon, watching the molecules and working the door. Every time a fast molecule comes toward the door from the left, the demon lets it through to the right. Every time a slow one comes from the right, it lets it through to the left. It does this over and over, sorting. Slowly, without seeming to do any work, the demon gathers the fast molecules on one side and the slow ones on the other. Fast means hot. Slow means cold. So the box, which started at one even temperature, would separate itself into a hot side and a cold side, all by itself, just from the demon's sorting. Heat would have flowed from cold to hot. The second law would be broken. Order would arise for free. It troubled physicists for a very long time, this little demon, because they could not quite say what was wrong with it. And the resolution, when it finally came, is one of the deepest ideas in modern physics, and it connects heat to something you would never expect. Information. Here is the resolution, gently. The demon has to know things. To sort the molecules, it must observe each one, measure whether it is fast or slow, and remember, at least for a moment, which way to open the door. And information is physical. It has to be stored somewhere, in some real memory, made of matter. The demon's memory fills up as it works, and to keep going forever, it must eventually erase that memory, clear it out to make room for more. In the 1960s, a physicist named Rolf Landauer proved something remarkable. Erasing information, wiping a memory clean, must always release heat. It cannot be done for free. There is a minimum amount of heat that must be spilled into the surroundings every time you erase a single bit of information. And when you add up the heat the demon must release to keep clearing its memory, it exactly cancels the order it was creating. The books balance again. The second law holds. The demon cannot win because thinking itself, remembering and forgetting, costs heat. Information and entropy turn out to be two faces of one thing. To know is to pay in warmth. That link between the spreading of heat and the erasing of information is one of the strangest and most profound things we have learned, and physicists are still working out how deep it goes. So heat is motion, and temperature is the average energy of that motion, and entropy is the spreading of it, and information is tangled up in the whole affair. It seems, by now, like a finished story. But heat still holds a few genuine strangenesses, right at its edges, and they are worth a gentle mention before we come home, because they show how much is still open. Here is one. You would think temperature has a simple ceiling and floor. The floor is absolute zero, no motion. The ceiling, you might guess, is infinity, endless heat. But physics has a stranger thing than infinite temperature. It has negative temperature, and a system at a negative temperature is not colder than absolute zero. It is, oddly, hotter than any positive temperature at all, hotter than infinity, in a sense. It happens only in very special systems, and it comes from the deep definition of temperature in terms of entropy and energy. It sounds like nonsense, and it is real, and it has been made in laboratories. It is a good reminder that temperature is a subtler thing than a simple scale of hot and cold. Here is another strangeness. Temperature is not really a property a single particle has. One atom alone, flying through space, does not have a temperature. It has a speed and energy, but not a temperature. Temperature only appears when you have many particles sharing their motion, settling into that spread of speeds. It is a statistical thing, a fact about crowds. So temperature, one of the most basic things you can measure, one of the first numbers a child learns to read off a thermometer, is not fundamental at all. It emerges from the behavior of many things together. A single particle is neither hot nor cold. Warmth is something the many do together, and it dissolves when you look too closely at any one of them. And here is the deepest strangeness, the one that sits underneath everything and is genuinely unsolved. We said entropy always increases, that things spread from order toward disorder. But that means that in the past, things were more ordered. Run it back far enough, and the early universe must have been in a state of astonishingly low entropy, extraordinarily ordered, for the whole long spreading to have somewhere to go. And nobody knows why. Why did the universe begin so ordered, so far from the spread-out state, wound up like a spring ready to unwind for billions of years? There is no accepted answer. It may be the deepest open question in all of physics, and it is the reason the tea cools and the reason you remember the past and not the future. The whole arrow of time, the whole one-way flow of things, seems to rest on the strange fact that the universe started in a very special, very ordered condition. Why it did is a mystery we have not cracked. So even this, the humble cooling of a cup of tea, opens straight down into one of the largest unanswered questions there is. That, too, is a story for another night. There is one more place this story leads, far off in time, and it is strangely peaceful, so it makes a gentle thing to rest against before we come home. If entropy always increases, if heat always spreads, if differences always even out, then follow that all the way to the end. Follow it not for years or millions of years, but for spans of time so long they make the current age of the universe look like nothing. Where does it go? It goes toward sameness. Slowly, over unimaginable stretches of time, the stars will burn out, one after another, with no new ones to replace them. The hot things will cool. The cold things will warm. Every difference in temperature, everywhere, will slowly even away. The heat will spread until it is perfectly, evenly distributed, until there is no hot and no cold left anywhere, only one uniform, lukewarm sameness, filling all of space. This far future is sometimes called the heat death of the universe, though it is really more of a heat spreading, a great evening out. When everything is the same temperature, heat can no longer flow, because flowing needs a difference, and without heat flowing, nothing can happen. No engine can run, no star can shine, no life can live, because life needs the flow of energy, needs a difference to feed on. The universe would not be hot, and it would not be cold. It would simply be even, and still and quiet forever. Every candle burned, every difference resolved, every pocket of order finally spread out into the calm. It is the ultimate destination of the second law, the place all the spreading is heading, so far away in time that it need not trouble you in the slightest. And there is something oddly gentle in it, honestly, when you sit with it in the dark. The universe is not racing toward fire or violence. It is drifting, ever so slowly, toward evenness, toward calm, toward rest. Everything warm is sharing its warmth. Everything is slowly coming to the same temperature as everything else, over spans of time beyond all imagining. It is the longest, slowest settling there is. And you are a small part of it tonight, a warm thing among cooler things, quietly sharing your heat with the room, the way the stars share theirs with the sky, the way the whole universe is slowly, patiently, sharing everything with everything, on its way to a stillness that lies almost infinitely far away. There is no need to fear the far end of that. It is only rest at the largest possible scale. And rest is exactly where we are going now, in a much smaller and much nearer way, back down through all of it, to the warm body on the bed. Before we make the last descent, here are a few small everyday things that all make sense now. Once you hold the idea that heat is motion that spreads, and they are pleasant to turn over as you drift. Consider the refrigerator humming quietly in your kitchen. It does something that sounds impossible. It moves heat from a cold place, its inside, to a warm place, the room, from cold to hot, the wrong way. But it does not break the second law, because it pays. It uses electricity to do the work, to run a pump, and it dumps more heat out the back than it removes from inside. That is why the back of a fridge is warm, and why a fridge with its door open will actually heat the kitchen, not cool it. It is Maxwell's demon done honestly, sorting heat uphill, but only by paying the full price in energy and spilling extra warmth as it goes. An air conditioner is the same trick, pumping heat out of your home and dumping it, plus more, into the outside air. Consider why a metal railing feels so much colder than a wooden bench, even though both have been sitting in the same room, at the very same temperature, all day. Your skin is not really a thermometer. It does not feel temperature. It feels the flow of heat, in or out. Metal conducts heat quickly, so when you touch it, it pulls the warmth out of your hand fast, and that rush of heat leaving is what you feel as cold. Wood conducts heat slowly, so it draws your warmth away gently and feels warmer, though it is exactly as cool. The metal is not colder. It is just faster at taking your heat. What you call cold is often just heat leaving you quickly. What you call warm is heat arriving or leaving slowly. Consider blowing on a spoonful of hot soup to cool it. You are carrying away the warmest air, the air that has picked up heat from the soup, and replacing it with cooler air, so the soup can shed more. And you are helping the fastest, hottest molecules escape as steam, which carries off that hidden latent heat we met with Joseph Black long ago. Consider why you shiver when you are cold. Your muscles are trembling on purpose, doing rapid work to generate heat by motion, the same way Rumford's drill warmed the cannon. Your body, without asking you, turns to friction to keep warm. And consider why a blanket works. It does not make heat. It only slows the spreading. It traps a layer of still air around you, and air is a poor conductor, so your own warmth cannot escape as fast, and it gathers, and you stay warm. The blanket over you right now is not warming you. You are warming you. The blanket is only keeping the second law waiting at the door a little longer. holding your heat close instead of letting it spread away into the night. And consider your own body, the warmest and cleverest heat machine of all. You are warm-blooded. That is a quiet marvel. Your body holds itself at very nearly the same temperature, day and night, summer and winter, whether you are in a warm room or a cold one. It runs its own furnace. Deep inside you, every cell is slowly burning the food you have eaten, releasing its stored energy, and much of that energy comes out as heat. That is where your warmth comes from. Not from the sun, not from the room, but from the slow fire of your own living cells, burning quietly every second, keeping you warm from the inside, and your body watches its own temperature with great care. There is a small part of your brain that acts as a thermostat, always checking, always adjusting. When you grow too warm, it opens the tiny vessels near your skin and sends up sweat, so heat can pour off you and carry warmth away as it dries. When you grow too cold, it pulls the blood back from your skin to save your heat and sets your muscles shivering to make more. You do none of this on purpose. It happens below all your thinking, faithfully, every moment of your life, awake or asleep. Right now, as you lie here, that quiet thermostat is holding you at your steady warmth, spending just enough of your slow inner fire to keep you exactly as warm as you need to be. It has never once stopped. It will keep you warm all night, without a single thought from you. So the warmth you feel under the covers is really two gentle things meeting. Your own inner fire, burning low and steady, making heat from the food of days past, and the blanket, holding that heat close, slowing its escape into the room. Between them, a small pocket of warmth is kept, exactly around you, exactly as warm as a body needs. You are a warm thing, tending its own warmth, wrapped against the cool. And that is a very old and very safe way to be. So let the whole long story settle now, gently, and let the people we met tonight drift off, one by one, into the dark. Let them go the way you let go of a day, the ancient ones watching fire leap and calling it an element, the careful believers in caloric, the invisible fluid, who were wrong in such a reasonable way, Lavoisier, writing heat onto his list of elements, Joseph Black, watching the ice sit stubbornly at its melting point, swallowing heat without warming. You do not have to keep their names. Let them drift. Count Rumford, boring his cannon in Munich, watching the water boil and knowing no fluid could pour out forever. Young Carnot, seeing the deepest truth of engines and dying at 36 with most of it still in a notebook. Joule, the brewer, churning his water with a paddle wheel, measuring warmth into existence, ignored for years, and right all along. Mayer, the ship's doctor, reasoning his way to the conservation of energy and nearly broken by being unheard. And Boltzmann, who saw furthest of all into the counting of atoms and staked his life on their reality and did not live to be proven right. They did the work so the understanding would exist in the world. Not so that you would have to carry it. Let their names go, like everything else. The understanding does not live in your memory tonight. It lives out there, in every warm thing, whether or not you remember a word of it. And let the confusion settle too, because it was never a problem to solve before you could rest. We do not know why the universe began so ordered, so wound up, that heat has been spreading ever since. We do not fully understand the deep tie between heat and information, between forgetting and warmth. We cannot quite say why the humble cooling of a cup of tea points in the same direction as the whole arrow of time. These are open questions, out there in the dark, being turned over by people who love them. And not one of them needs anything from you tonight. Let them stay open. They are a soft place to lie down. So let's come down through all of it now, slowly, back to the warm body on the bed. Start far out, at the very end of time, where the heat has all spread even, where the universe rests in its distant, lukewarm calm. Let that far, quiet ending stay where it is, almost infinitely far away. Nothing to reach you tonight. Come inward, past the burned-out stars of that far future, back to our own time, where the stars still shine, still pouring out their heat, still holding back the evenness for billions of years yet. Come to one ordinary star, our sun, a great slow fire in the dark, sending its warmth across the empty miles as light. Come along one of those rays, all the way in, to a small blue world it warms. Come down through the thin air of that world, the air that is itself a storm of flying molecules, each one hurtling along faster than sound, though you feel only a soft warmth and a gentle pressure. Come down to the night side, where it is dark, where you are. Come to the land, to the region, to the town, to the roof over your head. Come in through it, to this room, to the bed, to the covers, holding your warmth close, to your own body, lying here in the dark, warm, breathing, glowing softly with a light you cannot see, and rest there. You have come all the way down, from the far heat death of the universe to the warmth of your own chest. There is nowhere further in to go. Feel the weight of your body on the bed. Feel the warmth held under the covers, your warmth kept close by a still layer of air. Feel where you are heavy, where you are held, where you are warm. Let the far things go now. Let the heat death of the universe go. It is almost infinitely far away. Let the burned out stars go. Let the empty cold between the galaxies go. Let the sun go, that great slow fire in the day. Let the whole spreading cosmos drift off to the edges of the dark. None of it is here. None of it needs you. Let the near things soften too. Let the room fade. Let the walls fade. Let the still air settle. Let the covers grow heavy and warm. There is only this now, a bed, a body, a little warmth held close, and breathe. Feel the warm air move in and out. Feel it warm your chest and leave a little cooler. That is heat, moving gently, the way it always does, in and out, warm and cool, slow and slower. Feel your hands. They are warm. That warmth is motion, deep down, atoms trembling, too small to feel. Feel your chest rise and fall. Feel the soft heat of your own body, kept steady by a quiet fire you never have to tend. You are warm. You have always been warm. You will be warm all night. There is nothing to do. There is nowhere to go. There is only the warmth, and the dark, and the slow rise and fall of your breath. Let it slow. Let it settle. Let it carry you down. And now feel what that warmth actually is, with everything we have said tonight behind it. It is motion. Every atom in you is trembling. Right now, gently, faster than you can imagine. The warmth of your hands is the jiggling of their atoms. The warmth of your chest, of your face, of your breath, is countless particles in constant, restless motion, sharing their energy, bumping and passing it along. You are not a still thing that happens to be warm. You are a vast, quiet storm of motion, trillions upon trillions of tiny movements, all of them together, felt as a single soft warmth. To be warm is to be moving, deep down, everywhere, all at once. And you have been moving like this, atom by atom, every second of your life. Feel the warmth leaving you too, gently, into the room. You are glowing, not in any light you can see, but in soft infrared, pouring off your skin into the dark all night long. Your heat is spreading outward, as it must, as everything's does, into the sheets, into the air, into the night. And that is not a loss to fear. It is just the second law, doing what it always does, patiently, kindly, letting your warmth join the wider world. The blanket only slows it. It cannot stop it, and it should not. You are meant to share your heat with the room, the way the star shares its heat with the sky. And the atoms doing all this jiggling, all this warming, are ancient almost beyond thought. The very stuff of you, the particles trembling with your warmth, was made long ago, in the first minutes of the universe, and in the hearts of long-dead stars. They have been warm and cold many times, in many places, across billions of years, before they gathered, briefly, into you. The warmth you feel tonight is old motion, passed down through the whole history of everything, handed at last to the atoms of a body lying in a bed, wondering about it. You are the latest warm place these old particles have found to be, and your warmth is joined to everything around you, quietly, right now. The heat leaving your skin is warming the air, and the air is warming the walls, and the walls, ever so slowly, are letting that warmth seep out into the night, and the night is losing it, little by little, to the sky, and the sky, in the end, to space. There is an unbroken line from the warmth of your chest to the cold between the stars. You are one end of a gentle current of heat that runs all the way out to the edge of everything. Not rushing, just drifting, the way heat always drifts, from the warm toward the cool, from you toward the wider dark. It is the same current that carries the warmth of every living thing, of every star, of the whole universe, all flowing the one way, all sharing, all spreading, over unimaginable time, toward the great far evenness. And tonight, you are simply part of it, a small warm source, giving off its gentle heat exactly as it should, joined to all the rest. There is nothing to hold on to in that, and nothing to fear. It is only warmth, doing what warmth does. It is only you, being a warm thing among cooler things, sharing what you have, the way everything warm always has. So there is nothing you need to do now, and nothing you need to hold. The warmth will keep itself. Your body will hold its temperature while you sleep, without a single thought from you, as it always has. Your heart will keep its heat. Your breath will keep its warmth. The heat will keep spreading, gently, into the room, and the night, and the sky, the way it has since the beginning, and none of it, not one bit of it, needs you awake to happen. It will all carry on exactly as it always has, whether you follow it or not. It will still be here in the morning, the warmth, the spreading, the whole slow settling of the universe. And so will you. You do not have to remember any of it. There is no test in the morning. No need to recall caloric from Carnot, or Joule from Boltzmann, or which way the entropy climbs. Let the names go. Let the numbers go. The degrees and the speeds and the coldest floor you can never reach. All of it, out of your hands. It was never yours to carry. It was only something to listen to on the way down into sleep. All that is left, the only thing being asked of you now, is to lie here and be what you already are. A warm thing. A small, quiet storm of gentle motion, glowing softly in the dark, sharing its heat with the room, held close under a blanket. Breathing. So let your breathing slow. Let your atoms tremble on, warm and faithful, without your help. Let your heat spread gently into the night, as it is meant to. Let the whole vast universe carry on its long, slow settling, far away and all around, needing no witness, asking nothing. There is nothing to do but rest here, warm in your own gentle motion, in a quiet dark room, one small glowing pocket of warmth in the enormous cooling dark. Let the caloric go, that old invisible fluid that never was. Let the engines go, and the paddle wheel, and the boring of the cannon. Let the ink spread in the water and stay spread. Let the tea cool and never uncool. Let the far heat death rest at the far end of time. None of it asks anything of you now. It was only ever the story of your own warmth, told the long way around, so that you would know what it is that keeps you warm in the dark. And now you know. It is motion. It is old. It is gentle. And it will hold you all night. Feel it one last time. The soft weight of the covers, the still warm air beneath them, the slow rise and fall of your breath, warm going out, cool coming in, the quiet, faithful fire in every cell, keeping you exactly as warm as you need to be. You do not have to tend it. You do not have to think of it. It simply keeps you the way it always has and the way it will while you sleep. So let it. Let yourself be warm and held and still. Let the gentle fire burn low and keep you and ask nothing back. The room is dark. Your warmth is steady. The heat is spreading everywhere, gently, the way it always has, and you do not have to help it or understand it or stay awake for any of it. You only have to lie here and be warm and be held. So just rest now. It will all still be here. And so will you. Good night.